So welcome to the Winds and Currents webinar. Today we have Luke Kachelein from JPL, who's going to talk about work he did as part of his PhD thesis at Scripps on the diurnal cycle in the California current system. And he'll be talking about currents from high frequency radar and winds from the ERA reanalysis. So take it away, Luke.
Thank you so much, Sarah, and thank you so much for omitting the fact that you were my advisor here at Scripps. So yes, as you said, this is more or less just ripped from my dissertation defense talk that I gave in April, which was a talk that I enjoyed very much, and I think it was probably the best talk I've ever given. But I prepared very well for that. And this, I really didn't. I'm kind of just, I'm just going to absolutely be improvising today and basing it off what I remember, what I said. So this is going to be an adventure, but that's okay. We're all friends here. So let's see what we got. So let me shrink. We'll zoom in off to the side. So yeah, so as Sarah said, it's about the diurnal cycle and how we detect it in California current system from high frequency radar and comparing it to winds from ERA5. And this is the title of my thesis that I gave back on April 7th. So that's about where my memory reaches. And this is a high frequency radar antenna that I took a picture of a few years ago. That was a nice picture. I use it in every presentation now. So yeah, this is from the chapter 3 of my doctoral dissertation about wind-driven diurnal currents, and it is a work in progress currently, and that has the title of this talk, basically, just very creative of me, I know, and that is currently in preparation. So just a little bit of background, just about the different time and spatial scales of processes in the ocean, and where they fall along the cascade of energy line, basically. And let me see what I'm supposed to point out. Oh yeah, that certain processes occur at this combination specifically of length scales, basically the internal tide length scales. I was talking about a lot during my talk because that was a big part of what I did my doctoral degree on. But that's not really as relevant for today. What really is relevant is the ability of these different networks to observe these different processes in the ocean. So here's sort of the same time length chart, but with the capabilities of different observation networks overlaid onto it. And the only two I really want us to focus on is satellites in purple and HF radar in green. So these are the range of spatial and temporal and spatial and temporal scales that they're able to cover. And as you can see, there's overlap, but there's also parts of this domain where they excel in their own ways. And overlaying this on the first one, we can see what processes are best resolved by each of these technologies. And what we really want to focus on is what the HFR radar can see well that satellites can't. And so in order to prepare for either present or future satellite missions that will observe processes from the episcales, but not be able to resolve them. It's best we should use this other network, the HFR network, to maybe describe them better. And yeah, and I want to say that this green square that on the original publication that I cited it's too small in the spatial domain. It's bigger nowadays because of the expansion of the network. So basically, to sort of lay out our problem as it ties back to the instruments I was just talking about, is that diurnal daily winds and currents are energetic, and they pose a similar problem for scatterometry missions as tides do for altimetry. So what I mean by that is that basically they are too fast to be resolved by a typical satellite that would be observing this system. So to estimate wind and or currents from vectors from backscatter. That's the purpose of scatterometry missions, but we all know this is wind currents webinar. And they're usually sun synchronous, so actually they do they actually are capable of resolving the diurnal cycle, but not well. And because of that, because it's daily, which is as fast as the cycle is, so you're not going to get a very good picture of that. And in fact, if it is sun synchronous, you will end up sampling the diurnal at the Nyquist frequency. So you'll always be hitting it at its minimum or maximum or nadir, at a node, basically, or across a zero. And this is what you want to avoid, because then you have this entire energetic process that happens daily, which we know that the diurnal cycle is energetic. But if we hit it at a 0 point, that's not good. So that's sort of an operational, I guess, motivation behind this work, is to try to figure out what time of day is this, or what time in the cycle, which for us is what time of day we should be hitting, different regions, different processes. So we need frequently sampled data with spatial resolution, at least as good as satellites have, and that's where the HFR network comes in. And so just a little overview of the system, I guess, is probably due. I think we've talked about this already in not long ago in the webinar series, so I'll keep it fairly short. But basically, yeah, we have the antenna on the shore, pulse transmitted to sea, uses Bragg scattering, I think. Depends on the wavelength of the surface waves that are coming in, and it does a bunch of magic math, literally. It's called the sorry, not musical math. It's called the music algorithm, to basically figure out how the current is flowing to or away from the antenna, only in that direction. And that's a problem if you only have one antenna, but once you have two, you can do trigonometry to figure out which way the current's actually pointing. And when you have, say, 160, then you can really get a rich picture. So this is the growth of the network over the course of the last, 18, 20 years. And so, yeah, so it provides near real-time vector surface currents. I already said that. And it's then gridded to a nice little Cartesian grid that is much easier for us to just start analyzing. And just to compare, this is what one antenna sees. It sees only what's coming to or away from it. But when you put them all together and do some trigonometry, this is off the coast of New Jersey. When you do a bit of trigonometry and have a bunch of antennas up and down the coast, you can start to get this rich vector field. And you can see eddies, or probably some mesoscale eddies here, and other flows. And I just thought this is a good little demonstration of sort of the before and after the analysis happens. Their analysis, not ours. So overall, just to recap the motivation, we want to know when currents are at their strongest, their spatial structure, and their seasonality, and well, what else can we learn from this? So we want to, let me, by the way, overview of this chapter is comparing currents with winds, focusing on the diurnal cycle, examine when in the day both are at their maximum, coherence between the two, that's pretty important, and then look into the deflection angle between the two, which is, follows sort of from, or is related to like the basic Ekman theory that we're all taught in first year oceanography class, but actually doesn't really hold that well in the real world if you dig too deep into it. That's okay. So winds and currents, let's look at them in the spectral domain, in the frequency domain rather. And we have here a rotary breakdown. So instead of the zonal and meridional velocities showing their power spectra, it's all combined in a complex formulation to get the clockwise versus counterclockwise rotational power of each component. And so if one of these was, say, 1 and the other one was 0 or way less, you'd have basically a circular current. And if they're the same in magnitude, they'll be mostly rectilinear, so like back and forth in some way. And so there are differences between these two. You can see that because these measure the same quantity, meters per second, and therefore their spectral power density is meters squared per second squared per cycle per day. These are actually directly comparable values. And of course, the atmosphere just moves a lot faster than the ocean, so that's why this spectrum is so much more powerful. And we see that in winds, we have we have a strong diurnal cycle, and then we have notable harmonics going all the way down. Now, I have a feeling that the highest harmonics are kind of an artifact of something that's wrong with the data set, but the lowest harmonics are definitely real. And then we see in the currents, sort of something similar vaguely, but then we have these extra other peaks, which are due to the tides, which are not present in the atmosphere to the same appreciable degree. And then we have the near inertial response of the ocean as well, which is very much an ocean thing. And we see that that's strongly clockwise polarized because we're in the northern hemisphere. Nothing too unusual, but their background power slopes are also different. The atmosphere goes omega to the -2. And the ocean goes omega to -1, which is an interesting difference. I'm not entirely sure what it is. I'm sure that maybe some people who are more familiar with this sort of dynamics could probably explain it quickly, but I actually don't remember. So let's look into some of our findings. So what we did was we basically just used a least squares harmonic analysis to decompose the currents and the winds into a diurnal component and a bunch of other frequency components as well. But we're just looking at the diurnal today until the very end. We'll look at more later. But for now, just think about the diurnal, the 24-hour cycle. And what we have at the left is the mean summer diurnal semi-major axis length in color, as well as those black ovals. And then the white ovals are winter, the same value at the same location. And what we see is there is seasonality in the winds, and actually you'll notice it in most locations. The black ellipse, rather not oval, is the summer ellipse is greater than the winter. Okay, so there's some seasonality going on. But generally, the ellipses are oriented at pretty similar angles throughout the year. So there's a little bit of regularity, but not like completely uniform. And we actually see something sort of similar in currents as well. So this is the same quantity in currents, and you'll notice there's a resolution difference because this is a reanalysis product that has at a much coarser resolution, and this is it's also a product, but it's a much finer resolution just because that's how the network can observe it. And then this is a little cutout of SoCal bite because it's the ellipses get very big and overlapping here. But we also see very much the same seasonality that we do in the atmosphere as well. So where we have a stronger diurnal cycle during the summer than in the winter. Although interestingly, I want to also sort of notice is that the ellipses in the winter are sometimes bigger than those in the summer, whereas over here it's always the case that those summers bigger. And you'll also notice there's a little bit more variation in the orientation, but I don't know if that's necessarily important yet. But yeah, and another thing to point out is they're both intensified along the coast, especially the wind. Also the current, you can see it's pretty weak out here as you get farther offshore, and also very intense here in the SoCal Bight, which I think is curious because it's not like we really think of this as being a very windy, energetic part of the ocean. Because I'm originally from the Oregon coast, and it's way windier up here than it is down here to like your daily life on the coast. So this is just a very curious difference. Obviously, if you get farther offshore is when this actually happens. Near shore is actually kind of weak here in the San Diego region at least. So how strong are the diurnal processes? Well, I mean, I've sort of already given a hint of that. But yeah, it's stronger in the summer than in the winter, and this is just visualizing the fraction of total variance now, because, well, you could say, well, maybe it's much more energetic overall during the winter, and the diurnal cycle, just sort of doesn't play a big role. But no, actually, not just in terms of total magnitude, but in terms of share of total energy, we have more energy in the summer than in the winter for the winds, and also for the currents. And if I would say it's even starker for the currents, although maybe that's just because we have a smaller band of data to work with, and so our eyes sort of, maybe accentuate the differences a little bit more, perhaps. But still, this holds for both processes. And there was some other conclusion I was trying to come to, but I can't really remember. Oh yes, when are they at their maxima? So looking previously at those last two plots, we were only looking at the magnitude of the currents and the winds. So now the natural question is, well, what about the phase, which for us is just the time of day when it's at its maximum. Normally when we talk about phase of some process, we're talking about just where in the cycle, and we'll talk about it in radians or degrees, but for the diurnal cycle, because it's the cycle that our bodies are live off of, we can actually talk about it in terms of just hours or local time. So that's kind of nifty. And if we look at the decomposition of the winds and figure out what time of day it's at its maximum, which is on a 12-hour cycle because it's a 24-hour cycle, but it's sinusoidal decomposition. And then so we're only worried about if it's a maximum at 3 o'clock, well, it's a max at 3 p.m. and 3 a.m. So we'll just say 3 o'clock and not specify the a.m. p.m. And this is local time, so not just like Pacific time, but like instantaneous local time. Like you move a few kilometers to the east and your local time changes. But overall, I want to point out how for the wind along the coast, we have sort of a strong range around 4 a.m. p.m. And this is in both summer and winter. We see a little bit of shift a bit seasonally, not that strongly, but I would say it's the strongest seasonal shift that we see is here off, in Northern California. How it's sort of the peak hour in summer is yellow, which is before 3 o'clock, and then it shifts to after 3 o'clock and only 4 o'clock a year later. And that sort of is reflected in the overall shift towards a 4:50 a.m. p.m. Peak time of wind versus 4:03 a.m. p.m. Within 62 kilometers of the coast. And the reason I say that is because if you recall from earlier, the wind or the wind is the diurnal wind is so weak farther offshore, we might as well just look within some strip along the coast. And I chose 62 because that's 2 times the width of a grid cell. This is it's a 31 roughly kilometer grid cell here at this latitude. Now the behavior of winds is consistent with our understanding of the sea breeze and land breeze. This is the time of day that various studies that I wrote about in my dissertation that I don't think I included in this presentation originally predict or observe. But basically the heating and cooling, the differential heating and cooling between the land and the water is what sets up this land breeze sea breeze. And it's conceptually kind of easy to understand, but of course, like everything in nature, it gets really complicated really quick if you actually try to analyze it with any sort of rigor. But let's look now at the response, or rather the diurnal cycling currents, which we know is a response to the winds to some degree. And we get a very different picture here actually. During the summer, we get a much earlier time, but well, for one, across the entire domain, and this was only 62 kilometers from shore, but I definitely did this calculation both ways, and it wasn't that different that way. So I want to point out here how there is a whole range of different values of time where, during the summer at least, that the current is at its maximum magnitude, and it has a much bigger spread than any other of these 4 panels. And well, that's hopefully confusing or interesting or both. Because especially it's interesting because during the winter, it kind of behaves a little bit more like the winds, and it's a little bit more coherent, and it also basically a very similar time of the 12-hour cycle that it is at its maximum, with almost the same spread as well. So that's very curious. Well, why could this be? Well, actually, yeah, I don't have a slide on this. I looked into it more, and I believe it is because the eccentricity of the current ellipses is much lower, therefore more circular, during the summer than during the winter. And that plot I showed much earlier, I can jump back to really quickly. You can sort of see this, how the white winter ellipses are a little bit more stretched than the more circular summer ellipses. And when we have these more circular processes going on, the time of maximum is sort of more it varies more because they're really, if it's a perfectly circular cycle, every time is a maximum. And if it's slightly stretched out ellipse, which all of them are, then your time of maximum in the cycle will probably vary a lot based on just noise. So, because where on a very fat or where on an only slightly deformed circle is it at its maximum? It just depends on the noise term basically. So how coherent are the winds and currents? Well, we could look at the coherence of the meridional and zonal components, and also their cross terms. But what we're actually going to do is, of course, because we've already started with a rotary power spectrum and these processes are strongly polarized, then we are going to be looking at a rotary coherence, which is something if you don't regularly calculate rotary spectra and/or coherence estimates, then there's a lot of sort of thinking your brain's got to do to really understand what's going on. But basically, how much is a clockwise component of one process, how much is statistically related to the clockwise component of the other processes, and vice versa for counterclockwise, as well as their cross terms. So we're going to ignore the cross terms because, well, basically we don't expect there to actually be very much physical relevance to it, and also it's from the plots, the analogous plots, there's not very much going on. Instead, we're going to look at the coherence of just the clockwise terms with each other, because both the winds and the currents are strongly clockwise polarized from the northern hemisphere. It's the 24-hour cycle. It's not too surprising. And these are the results we get for summer for these 2 panels and winter for these 2. So we have the coherence amplitude and the coherence phase, or the phase of the coherence in this continuous color bar. And I want to point out that they are fairly similar both times a year, but there are some minor differences. Minor differences. Namely that in the summer they're more coherent, than in the winter. Not by much, but you can sort of appreciably see there's a darker shades of red along most of the coast, as well as farther offshore than here, where it starts to actually become statistically incoherent with each other, the two processes. Except in this region off the coast of Southern Oregon, Northern California, where in the winter it seems to be more coherent. We're not entirely sure why this is. And discussing phase, well, it seems that the phase here is more pink, whereas in here it's more blue, which of course corresponds to specific ranges of time. You can see along here. And here we are talking about phase, not like the times when they line. So we are back on the 24-hour cycle. This is the phase difference. So how much the current leads the wind, I believe. We'll figure that out in a few slides. I wrote it down. But I also want to point out one more thing is that the Southern California bight is essentially identical for these two. All the big changes between the phase, as well as mostly for the amplitude as well, but definitely the phase is the same for here, and all the changes for the rest of the coast. So, but the process overall, avoiding these little, looking past these nitpicky little differences, they're very coherent. Now, does their phase translate to some sort of physical angle? Well, yes, it does. Yeah, it is currently wind. So this is an overview of the deflection angle of diurnal current from diurnal wind. The way that I define it here, and I'm sure that maybe some people here have maybe a different idea of how better to define it, because you've probably written papers on this since I was a young child. We have the maximum wind blowing in one direction, and then we have what direction is the current pointing relative to maximum wind at this time when the wind is at its maximum. And then, so then we calculate the angle between the two. And the reason we choose maximum wind is just because, well, that's when we expect at that time for the wind to sort of be as most influential on the current. So that's maximum. So we see more variation near the coasts in the summer. We see it goes all the way from red to turquoise. So like a totally opposite directions all the way to like parallel. But still mostly sort of, if we were to make a histogram of all this, it would still sort of start to coalesce around this 45 to 90 degree range. And the distribution of angles shifts seasonally. So in the winter, if you look at the same locations, there is a difference in the angle between the two, between summer and winter, or from summer and winter. And so the shift might point towards something interesting. Oh, and I also want to, if you're concerned about the sort of pixelation that you see along here, in both panels, and probably saw it earlier as well, that's just the pixelation from the ERA5 product, sort of trickling through, because this is on the resolution of the it's on the resolution of the HFR grid, but the ERA5 is what we're comparing it to. So we're going to get it's gridding as well, influence in here. But there's very little seasonal change in Southern California bight. These two processes are essentially the same. And this, I want to emphasize, I'm using the same color bar, but this is not the same quantity I was showing before, the phase difference. This is a different quantity, but they're apparently highly related. So what do we expect? Well, classical Ekman theory, a steady wind over the ocean, which again, steady means not on a diurnal cycle. It's not on any cycle. Classical Ekman theory predicts a 45-degree deflection at the surface, and that's all we are able to observe with HFR. And the wind is the product we have is at the surface. That's what we're concerned about. But we see this 45-degree angle at diurnal only regionally. So in Southern California, sorry, let me go back. Southern California, so 45 degrees is sort of this dark blue, but sort of more like a teal blue. And that's pretty much most of the SoCal bight, especially say off Los Angeles County. You see a 45-degree diurnal only regionally, yeah, that's it. And there are more sophisticated models than Ekman. They're still idealized, but they sort of account for more stuff, basically. Now, if we want to look at this deflection angle averaged over the whole domain, like at different frequencies than just the diurnal, say lower frequencies that are sort of more approximating that steady state that the Ekman theory describes. Then we get this. So again, summer on the top, winter on the bottom. This is, as a function of frequency, the average deflection angle of current from the wind across the domain that I've been showing this whole time. And red is the inner 90% of that range, and then black is the interquartile range, the inner 50%. So we have this interesting tendency for the angles to be sort of closer to zero at very low frequencies, and then get greater than 45 degrees as frequencies. But the diurnal being sort of an exceptional case where a lot of it is that offshore almost 90-degree angle difference that we see a lot here. So that's sort of like the purple color. But we don't really only see it offshore. If you look closer to shore, which I don't have the plot for right now, then it starts to collapse closer to 45 degrees as we expect. And this dark gray is the best performing model of the more sophisticated but still pretty idealized models that one of Sarah's students back in 2009, Shane Elipo and Sarah together wrote a paper on, and basically just to sort of show the difference. So Ekman theory is just a step function. It'd be 45, 45 all the way, and then at the inertial frequency, it shifts down to negative 45. And then this theory provides sort of a smoother transition. So I guess, what does this deviation in deflection angle mean, both at the diurnal as well as at all frequencies? Well, the diurnal, which has some of the largest deflection on average, is the influence of diurnal heating in the mixed layer, because there's a strong diurnal cycle in there, and that doesn't really exist at the other frequencies we're looking at. So that makes the diurnal unique among all these frequencies. But at the other frequencies, as well as the diurnal, the deviation is similar to previous observations. So from drifters, for example, we have, is it because the difference between offshore and nearshore depth varying vertical eddy viscosity? Maybe. Is it wind induced Coriolis-Stokes forcing? That's kind of my favorite choice, but again, that's just a feeling. And is it to do with complex vertical eddy viscosity? That again, like in the first bullet point, could be regionally varying. Well, we don't really what we want to talk about today. So I guess the conclusions for this chapter of my dissertation were, winds and currents both have similar diurnal components, similar times of peak amplitude, but different spatial distribution. They're highly coherent with each other in most regions, including as you go pretty far offshore, as they both get weaker in amplitude. So that's pretty notable, I think. Currents are deflected ahead of winds as expected, but greater than theory suggests. And the future work is addressing mechanisms that modulate deflection angle. Oh, and I want to say something really quickly back here. What I said, oh, they're highly coherent. That's surprising, because you may say, well, they're both diurnal processes, so of course they're going to be coherent. Well, when you're averaging over 9 years, like I did, I forgot to mention that. I averaged over the course of 9 summers and 9 winters. If the signals are, if the diurnal cycle is kind of, not that coherent with itself from year to year, then you wouldn't expect this high coherence. I do think some of this coherence is just because the diurnal cycle is so ubiquitous, but I guess that's for us to decide whether or not it's just a coincidental coherence because they're both highly ubiquitous, or if there really is more of a relationship going on that we're starting to tease apart here. And then I think it's both. So I think I'm done now with that sort of very rambly improvised talk. So let's actually have this be the discussion that it's supposed to be, not just me giving a lecture. Because if it was me giving a lecture, I've kind of failed. But if it's starting a discussion, I think I've succeeded. So what do we got?
Well, thank you, Luke. This was great and definitely seeds a good discussion. We'll open the floor up for questions. And maybe while people are thinking, I'll just go back to your signals showing the diurnal wind propagating offshore, because that's such a wonderful and clear signal.
Yeah. Oh, yes. Yes. Thank you.
And I think it really lays the groundwork for thinking about how to optimize the overflight time for a sun-synchronous satellite.
Yeah, thank you, Sarah. Yeah, I mentioned this a lot in my dissertation because, oh, Shane, you're on the call. Yeah, I would have mentioned you by name, more prestigiously than I did earlier if I saw your name on the list. Sorry. B has her hand raised too. Well, I think Shane got there first. So Shane, you start.
Hi, Luke. Thank you very much. Yeah, so the high coherence that you notice is amazing. I'm kind of questioning it a little bit. So, but if it's a truth, if it's a right signal, that's pretty cool. Why did you consider only the clockwise component? Because the reason why I'm asking you this is that the physical interpretation of the phase being a physical angle between a rotating wing being circular and like the rotating current is fine, but then in effect, like the motions are actually elliptical, right? So I didn't find this out, but some people before me found out that what you actually need to look at is the half sum of the positive and negative and the half difference of the positive and negative. And so I forgot which one is which, but one is giving you the time mean orientation between the two principal axes of the wind and the currents. And then the other quantity gives you the time lag, which is basically the difference in time at a single frequency between, you know, the maximum of one ellipse and the maximum of the other ellipse, right? So this is how we distinguish the difference between the geometrical component of the phase and the temporal component of the phase. And I think one of the reasons why, you know, this is actually the case, if you look back at the plot that you have that shows a phase as a function of frequency for the clockwise component, right? So you did notice a tendency that goes from, you know, 0 to higher frequencies of having an increase of the phase. So this is very characteristic of a constant time lag that manifests itself as a linear dependency on frequency for the phase, right? So if the phase changes linearly with frequency, which maybe it is here doing but you can't really see it because it's on the log scale. Yeah. But if you actually find a constant slope as a function of frequency, it shows you that you have a constant lag, you know, independent of frequencies. So this is why I'm thinking that your phase information here is mixing both time and geometry. And
I want to comment on that. Yes. So I do, these are all very good points, and I'm glad it's being recorded because I'll probably look back at this later because we're writing, you know, I'm going to write this up after I submit this other publication that we're hoping to get submitted soon, and then I can start work on this more substantively. What I will say is I did look beyond just the clockwise. So I did all 4 possible combinations, and I'm only plotting these because, well, actually, you know, I should have probably just, for this presentation, I should have probably gotten all of them just to show, because I cut that out for my dissertation because, you know, there's only so much time, but we have more time here. So no, there was the clockwise, the counterclockwise. Okay, anything involving counterclockwise current actually wasn't that coherent, interestingly enough. And then the counter rotating components felt less physically relevant to display. Trying to remember though what they all look like, but yeah, I have like 2x2 panels of these quantities in the papers in preparation. I can share those with you at some later date.
I agree with you. The outer coherence, which is a coherence between the opposite component, I don't see a physical interpretation.
Okay, good. I'm glad we agree. Okay, we agree on that. But yeah, so what you were saying earlier about, yes, this does mix geometry and time sort of in a very messy way, and yeah, so this is just the deflection angle when the wind is at its maximum, which, as you know, is agnostic of direction. Not really, because we know it's overwhelmingly clockwise dominated, so we know these positive angles mean that the current leads the wind. But you could certainly imagine, you know, if they were both counter rotating and then the wind was leading the current, then it would look the same. What you said, I'm still trying to process this, but I think that is a framework that maybe I should consider, Sarah, you know, maybe we should consider actually putting in that paper. It's a little bit more vigorous than what I did, because this was my chapter 3 of my dissertation that was sort of rushing to finish so I could defend.
Yeah, I mean, you can look, you know, you can look in the papers we published with Sarah in 2009, okay. And then you may have some more details in my dissertation actually from 2006.
Okay, good. All right.
Good luck. Looks great.
Providing commentary on a more sort of rigorous analysis that we can do for this, because yeah, you're right, there was a little bit of mixing up of stuff going on. Okay, I think I answered everything. So Bia raised her hand next, and then Ali later after. Hi, Bia.
Hey, Luke, that was great. Thank you.
Thank you so much.
A quick question. I know you kind of had to use ERA5 to get those spatial structures, but how does that compare with, let's say, buoy wind?
That's a good question. So I did make sure there was, for some reason, when I was doing this analysis of the wind, I had my doubts about the wind, or I wanted to verify. So I did compare to like 1 or 2 wind buoys, and they seemed to be pretty similar, just visually comparing the time series, basically. I didn't do any vigorous analysis. They seem to be pretty reasonably similar, but that also makes sense because I think the wind buoys contribute to the ERA5. So, you know, if it's being reanalyzed, and especially, you know, the closest quantity in the whole reanalysis product being, you know, surface wind to the buoys, you know, then they should look similar. But they visually compared favorably, but again, that's very non-rigorous, and also, sort of just based on eyeballs and like 1 or 2 points. So that's maybe answered your question, not satisfactorily, but I did look into it basically. Anything else? Guess not. Okay, Ali Reza has their hand raised.
Hello, can you
Hello.
hear me?
Yes, now.
All right, so it was a nice talk, thank you.
Thank you.
I wonder if there is a way, I wonder if it is possible to clarify the contribution of tides and winds in the generation of these diurnal cycle in currents.
So let me see. So I know that there is technically a 24-hour tide, the S1, but that is very, very weak compared to all other tidal constituents. Whereas in this signal we see, if we compare it to tidal frequencies, it's actually quite strong. And so we expect the diurnal currents to be very overwhelmingly due to the diurnal cycle, due to the wind, basically. But maybe you're commenting on other tidal cycles that are nearly diurnal. We have a long enough record that our harmonic analysis is able to unambiguously isolate 24-hour cycle compared to, say, the K1, which is almost, it's the 20. So the K1 is the 24-hour cycle plus the annual frequency. So it's just a little bit off, but we have sufficient resolution to do that. Yes.
So you mean that the dominance frequency is S1 if we do the harmonic analysis? It's the S1 which is dominant in currents?
Yes, but not the S1 tide. It's at the S1 frequency, which we sort of play fast and loose. If we or I play fast and loose with the language. I use these Darwin terms, so Charles Darwin's nephew, I think, or son, was the one who invented these, M2, S2, K1, P1, O1, whatever terms. But so yeah, here in the currents, the 24-hour cycle, we should say, is strong, but that is almost certainly not due to the tidal cycle, because the 24-hour tide actually doesn't really exist very much. Really, the diurnal tide is mostly the O1, which you have a big peak over here, and the K1. Am I getting these right? Have I already forgotten all my tidal things? I'm sorry, I haven't thought about tides for about 2 months. Or I haven't thought about exotic tides outside the M2 for a while. But yeah, so it should not be the tides. This should just be diurnal. And actually, that's a good question, because I made similar plots to these coherence for tidal constituents that I did not expect there to be any coherence, and as expected, there was not any coherence, not significant coherence. So, for example, the M2, which is not a wind it's not a frequency that's strong in wind, but it is a frequency that's a very strong occurrence. We only saw spurious correlation. Excuse me. I can say very confidently that we're looking at the wind-driven component of the current and not a tidal-driven component. Is that answering your question?
Yeah. Can I ask what was the length of your data when you were doing the harmonic analysis? Because we also have like K1, which is very close to S1. They are very close. So you should have a very long period of data to be able to distinguish between K1 and S1. Yeah,
to distinguish K1 and S1 properly, you would require 2 years of data, if I recall. Because if it's a one annual cycle difference between the two, then you'll need 2 years in order to get, like S1, the thing between, and then K1. So that's a good point, because the analysis we did was over 6-month windows and then averaging them all together to get a coherence analysis for the seasonal cycle. And we may say, well, 6 months, that's not nearly long enough, and that's true. We are averaging, though, over the course of 9 years. So any incoherence in the K1 would probably be averaged out. That is worth looking into. So what one could, I suppose, do is look at 2-year chunks and do a coherence analysis on that to tease apart the difference between the K1 and the S1, and then sort of ignoring the seasonal cycle and seeing if that does anything. But what I will say is, I would guess, this is a thorny question, because the K1 is at this frequency. We can't see it on here, but you can just imagine, the S1 plus a little bit is the K1, And that's a tidal signal, although it's not very strong, really. I wish I could zoom in on this plot, sorry, and show you the scale of the two peaks, the S1 and the K1. But it is much weaker. But you're right, it could still be influencing things. But I will say that because it is not present in the wind, we know that, then that whatever like the sort of the phantom K1 in the wind is, which is to say the background noise, would be so incoherent with the presumably coherent K1 tide that we would then sort of get that coherence to sort of cancel out. So I think it's, if anything, whatever K1 influence is in these plots is probably bringing down the coherence. At least that's my guess. But you're right, it merits a more rigorous. Why am I getting these words confused? I know the difference between the two. A more rigorous analysis going forward. So thank you for commenting on that. I actually didn't think that hard about it earlier, even though I knew in the back of my head what was going on.
Luke, if I can interject, I think one of the thorny questions that we were pondering about S1 is that so much of the world we live in is diurnal. And so the possibility that not just wind, but radiative forcing might be driving this is something that would merit further exploration.
Yes, but I think, as Ali said, that, you know, making sure that we're at least unambiguously not having any sort of K1 influence is important to at least comment on. Man, this is great. I'm gonna save the recording to my hard drive just so when we're writing this paper in, you know, a while, we have this resource. All these smart people. Eric, I believe, is the next person to raise it. Unless
hi, you hear me?
Yes.
There are a lot of harmonics. Are these are these phase locked to the primary, and what is there information in the harmonics about what the dynamics is?
Okay, so that's a good question. There is a plot somewhere buried in my manuscript that is a little bit more illuminating in this point. So basically, this is sort of not really a companion paper, but sort of like this spiritual brother to another paper that you know, Sarah is rightly waiting on me to finish, which is almost there, mind you, about tides and sort of a very different but related analysis of tides. And where we look at a lot of tidal constituents because we're fitting over an entire 9-year window, so we get super high frequency resolution, or high resolution and frequency rather. Whereas in Fission, because we're looking over these shorter windows, we're looking at way fewer frequencies, because we don't want to have them too close together, because then we're starting to violate our Rayleigh criterion of how far you can resolve two frequencies based on the length of the record. Can
you flip back to the spectra that shows all the harmonics?
Oh, I'm sorry. Yes. Well, this doesn't show the harmonics; it just shows the power spectrum.
But this shows the harmonics.
Yeah. So what I did was basically for this study, because we're only looking at much shorter windows, 6 months, I fit to each of these peaks as well as a few others if they're resolvable, and a bunch of low frequency stuff just to sort of account for it. Well, actually, if you recall the very end, I'm not going to scroll there because it's going to take me like another 30 seconds, but you know, all those phase angle differences that Shane was talking about earlier, you know, so that I fit to all those frequencies. Actually, yeah, that's a good, because that actually I'm going to go to the end. Sorry, Sarah. Why did I have so many animations? Anyway, yeah, these are frequencies I fit to. So like a couple clustered around the semi-diurnal, or sorry, diurnal. A couple clustered around semi-diurnal that I'm not, that only one is being plotted, and diurnal and several others. So these are frequencies I'm directly fitting to. And you said, are they phase locked? I mean,
they have to be phase locked if you're just doing lines. So that, never mind that.
Yes, of course. Yes, but one could imagine, you know, fitting several frequencies side by side to sort of resolve like band pass, I guess, almost, that range of frequencies. So I'm sorry, I think I just went off on a tangent, and you had a question. I sort of
the question is there anything else you can learn about this from looking at the harmonics? And I guess this figure probably answers the question, sort of.
Yes, especially in a more rigorous analysis like Shane was talking about earlier. Would probably
I guess you could say that since the curves that don't lie within the error bars of the gray curve is this first harmonic, that tells you something pretty important. I don't know what it is.
Yeah, this lowest frequency harmonic is the I want to say that might be the 6-month cycle, which is a fundamental for this window length.
No, I meant the two cycles per day.
Oh, the 2 cycles per day. Okay, sorry.
That's the one that deviates.
Yes, it
a lot. So that
does.
tells you
And
something.
yeah, I think that a bit. So that's the S2. That's the 12-hour cycle, and that is a very tricky cycle that I try to avoid talking about too much in my studies because it is actually substantially contributed to by both. So the first harmonic of the diurnal cycle, which, as we know, is wind-driven and or radiative heating driven, and the S2 tide, which is the tidal signal from the sun. This is solar semi-diurnal. So there's 2 independent processes that are going on at the exact same frequency because they're related to the Earth.
But I guess what I was driving at is if the diurnal response is at all nonlinear, there will be a harmonic, even if there was only forcing at the diurnal cycle. I guess that's what I was getting at.
Oh, I see. Yeah. So if you have forcing the diurnal, you'll have the harmonic at the first diurnal, and you'll have a response at the first diurnal because it's the harmonic of the response at the diurnal. Yeah.
And a linear model wouldn't do that. For instance, classic Ekman layer wouldn't have a harmonic.
True, but as you noted, this has such a spread that it might as well just be noise. And I think this is because of the tides. I think the tides is making this too incoherent. Or rather, it's okay. I'm remembering the analogous plot to this one, but for the S2, and it has a lot more spatial structure in the coherence and the angles. It's a lot messier, but it's not as incoherent as like a pure tide that has no wind component as well, or the wind is not strong at frequency either. So so I really think that this wide error bar that you see here is probably due to the tides muddying things up, and because if you imagine just a purely incoherent process, it would actually probably look like this or this. The error bars are wide enough that if it's a uniform thing, I have it still, so the mean would revert to 0 and the error bars would be about that size. So I think it's the tides that are messing that up, but there might be some nonlinear thing that you said.
Okay, thank you.
Ali, did you raise your hand for a separate question, or is it still raised? I just want to make sure that everybody gets a chance to say something. Oh, and then in the chat message, Rick Danielson says, not sure how well ERA5 captures solar semi-diurnal tide, but it would be larger closer to the equator. Yes. Well, I guess I could look at the global to find that out. Are there any other questions?
Yeah. Other questions?
Or maybe some astute observation by Sarah that totally explains something that I obviously should have included.
I think the only thing I'll notice that Eric's probing about the non-phase locked might be a query about your other manuscript.
Oh yes, the one that I just have to revise a few paragraphs in the results section before I can probably submit it. And
but there is a detailed analysis of non-phase locked M2 tide.
Yes, but we sort of did it in a we sort of did that in a sort of kind of I'd say brute force way where we just fit a bunch of frequencies that are close to each other, but we can resolve because of record length. And then we just sort of, treat that as a non-phase lock part because it is slightly off in terms of frequency, and therefore it's going to be off in phase. Sorry, sir, I didn't mean to cut you off. It's the travails of virtual communication. We all know. We've been doing this for years. Was there something you were trying to say that I
No, that's perfect. Okay. Well, if there are no other questions, we'll thank everyone for participating. A great discussion. Thank you, Luke. And I'll stop the recording.
Yeah, thank you so much, all. See you all soon. Some of you I'll see in person this Friday. I'm going to be there for